nanoscience and nanomaterials. That is topic for us today. Okay. So the word itself says, what is nanoscience or what is nano? Nano is something that you are studying about it yet a particular length scale, then you say it is nano. If you are studying science in particular length scale, it is nanoscience. If your technology is limited to a particular length scale, it is nanotechnology. So technology is in that particular length scale. So what is key here is nano. The terminology of nano is key. So let us understand what is nano, then we'll go to nanomaterial, nanoscience and technology and so on. Nano is 10 power minus 9 meters. You also know centi. Many people have the confusion of this. It is sad to see that many people are not doing correctly in the laboratory observations also because of these conversion issues. Okay. Centi is nothing but minus 2 meters and milli. Some of the lengths you need to know. Minus 3 meters. Micro is 10 power minus 6. Then comes nano 10 power minus 9. After that, pico is 10 power minus 12. Then femto 10 power. Angstrom is nothing but, yeah, that is another kind of unit. 1 angstrom is equal 10 power, yeah. These are other side. This side also you have centi. Opposite to that, opposite to 10 power minus 3 is 10 power 3. Kilo. Symbol small k, right? 10 power 6. Yeah, mega. Symbol milli takes small m. That is the difference. Don't use the way you want. Kilo always small k. Capital K goes to the temperature, Kelvin. Okay. Then 10 power 12, 10 power 15, 10 power 9. Here it is there. 10 power 9 giga. Capital G. Right? So our technology now is in the range 10 power minus 9 meter length scales. You are talking about the length. So let us understand about the length scales. Human or other people like dogs or whatever, observable things with our eye. So it is in the which range now? Meters range. 1 meter, 2 meter, 10 meters, something, right? So we are in meter range. So it is a classical physics. Classical physics deals with the macro objects, bigger objects. Okay? A ball, cricket match is going on, ball is hit by the batsman. Then if you want to see the dynamics, it is classical physics in terms of meters only, right? From there, we are going down to micrometer, nu m. If you want to use the symbol micrometer, there is some length scale and also nanometer. In between, you have various bacteria, slightly bigger, virus, DNA. These are all nanometer size. This is slightly bigger than the nanometer, and some other will come in between. Right? Just for us to feel it, where we are. But now we are not talking about these things. Our aim is to study. Even if you want to study about a bacteria or a virus or a DNA, you are going to the nanometer region. You are studying in nanometer range. Okay. So what is the scale range? 10 power minus 9 meters. Or else, in specific, you need to study in between 10 nanometer to 100 nanometer. The study of science in this length scales, you can say it is nanoscience, or the technology in this length scale is nanotechnology. Okay. So because 1 kilometer also you can express in terms of nano. Sometimes yes, no. You can divide and multiply using 10 power minus 9. No, 1 lakh nanometers doesn't make sense. Okay, bigger number actually, right? So because nano terminology is so important, everybody started using that terminology. Okay, I prepared nano particle, but what is the size of the particle? They will say some 10,000 nanometers. 10,000 nanometers is bigger actually. It is not nano. Okay, it has some other name. Instead, they are tricking the words. Therefore, it is important. The length scale between 1 nanometer to or else 10 nanometer to 100 is basically, you can consider this as your nanometers, not everything. Even above 100, people say it is nanometers. Still, some we cannot accept, but physics sometimes changes below 100. Okay, so if the particle size is limited between 100 to nanometer, we say it is mesoscopic. Me or may? Mesoscopic or meso? Huh? What is it? Meso, right? Not me. Mesoscopic. If it is greater than 100 or else 100 to 1000 or 1 micrometer is macro. Micro level studies. These are the macro level studies. Macro means bigger. Compared to meso, this is bigger. So even it is your length scale, though it is in micron range, I call it is macro because it is bigger compared to meso. So the physics changes in this length scale to this length scale. Very different physics applies at these two length scales. Same object, but complete physics changes because of the change in the reduction in the size. Therefore, it is important. So another way to define nanomaterials is a critical length at which your physics changes. Okay. So if the physics changes at below the critical length, okay, you enter to the nano region. That is another way to understand. So this is the basic nanometer definition. In this chapter, we are going to study about the materials which are having lesser in size. When I say lesser, in this range, mesoscopic limits. The technology is very important in these limits. Today, we are actually moving, we are trying to scale down till where? When the first transistor built, it was this much bigger, in this room size bigger. It is very difficult to carry to the other parts. Okay, it occupies a lot of space. We reduced it, tried to reduce. Today, in small phone, you have billions of transistors. So as the number of transistors increase, the performance also increase. The space it consumed reduce. Okay? So the nano materials are very powerful. We are going to mid range to the micro, then to the nano. Nano is also we are trying to overcome and going to even more further downscales. Right, let us try to understand what happens if you go to the nanoscale, what kind of physics it changes, why it changes. If you want to prepare nanomaterials, how do you prepare? So some parts we will touch, then we can close it. Right. We will have some historical perspective before we go to the preparation of the nanomaterials. Because it is very important to realize how nanomaterials play in human life. Some of the historical perspective. which means when do we know about nanometer perspective? Yeah. Nanomaterials are not new for us, though the technologies we developed very recently to visualize them. They were there, though we don't visualize in the past. So it started long back. We need to take some of the examples. If you go back, one of the things people actually remember is about Romans. Roman kingdom was one of the famous kingdoms. They ruled whole world. Romans. Today it is sort of US is dominating. Previously Romans were there. Okay, then Greeks came. That's how Alexander was there. But Romans they ruled entire world for long time. Okay, so the Roman dynasty, they used to have beautiful constructions, and also some of the architecture is very good. They are known for that. So during the Romans time, which means we went to almost 16th century, 16th or 17th century. So some of the examples to cite is the colloidal metals they used. Where did they use? For the dye fabrics. Okay. So for the in the case of Romans, for the dye fabrics they used, because they are very fascinating about different colors the dress they wear. Okay. So the colloidal solution is basically nanoparticles dispersed in some sort of liquid that they use it for different colors of their dresses. Okay. And also to give the shining, or also to enhance the durability of the clothes. So dye fabrics they used nanoparticles, and also to color the glass, different colors for glass. Next one, in medicine also they use, especially to treat some sort of disease, arthritis. These are some of the historical perspective from Romans era. After the Romans, we should talk about Michael Faraday. This is very important. Michael Faraday contribution. Before Michael Faraday, one priest was there. His name is Antonio Neri, 1612. Antonio Neri. In the year 1612, he synthesized, or he developed a method of preparation of gold nanoparticles. He was basically a chemist and also a priest in the church those days. They used to do both the jobs. So he proposed how a gold particle can be prepared in the laboratory. After that, Michael Faraday was the one who prepared that in the laboratory, but it is in the year 1857. And he studied, he identified the nature of the gold. So what is gold for us? How does gold looks? It is precious, of course. So gold is shiny, right? So if you go to the jewelry, you will look for, okay, whether it is shiny or not, some of the properties. Let me read this statement, very interesting statement made by Michael Faraday. I am reading for you. Gold is reduced into exceedingly fine particles, which becoming diffused produce a beautiful fluid. Then he continued, the various preparation of gold, whether ruby, green, violet, or blue, consist of that substance in a metallic divided state. What he is saying is, okay, gold can be prepared, and he says different colors of the gold are appearing. He mentioned the colors as well: ruby, green, violet, blue. But why these many colors are coming? He says the metal is divided. Some substance is there, that metal is divided. Divided means no, something is happening. As it is divided, the colors are changing. That's a beautiful observation about the nanoparticles. So gold in the bulk it shines, but when you reduce the size, this was basically observation made in year 1857 itself. So when the size is being reduced, the gold lost its shininess. It turns out to be different colors. It becomes violet, ruby. Okay. So at different length scales, that is the first observation of Michael Faraday. So one question you also need to remember is, what are the nanomaterials? Usually this will come, and pick up example of any metal to show that nanomaterial behaves differently than its bulk counterpart. You can take the example of the gold. At what length scale, what color comes? You need to see and write it, right? Yeah, this is one of the example from the Michael Faraday. He said gold has different colors at different length scales. After that, one wonder was there. That was Damascus sword. Damascus is a city name. Anybody heard of this one? Sword? Hmm? Knife? Dagger? Yeah. Where did you hear that? It a video. What is it? What do you know about it?
Was preparing a Damascus dagger with a meteorite.
With a
Meteorite. Meteor. Meteor.
hmm.
Was preparing a Damascus dagger.
Hmm? It has patterns. Good. What patterns? Waves. Okay. Partially.
Basically, like the British from that iron and this what is
So this is one of the miracle because you have seen in Bahubali, he comes to sell some of the swords. He says, no, the sword is very stronger and no, you cannot break it. But Katappa easily breaks it. Do you remember that? But Damascus sword was actually very, unbreakable kind of thing. Not just, it is very light in weight. Not only that, it is flexible. Having all those qualities in single sword is very difficult. So it attracted researchers' attention. They prepared a special kind of sword to fight the battles. So how it is being built, that was one of the puzzle. Recently they examined a piece of the sword, examined and seen that pattern, actually patterns are there, not just the patterns, they are actually nanoparticles and nano rods. Nano rods are incorporated in that. So take a metal, on the metal you put nano rods of another metal. So when you have that nano rod kind of, after reducing the size, the structures, the flexibility improved, the toughness improved, it became more hard and strong. All the properties came due to the reduction in the size. They were not knowing about all those things. There were no systematic studies, but the sword was very famous. A recent article is published in Nature Physics on the same thing. Even in India, they say that they prepared one sword long back. What they used to do is, at the elevated high temperatures, they used to add some nanoparticle impurities unknowingly, okay, to increase the stability of the sword, right? So yeah, these are some of the historical perspective where we can see nanoparticles and their usage in their own technology on those days, right? With this idea, let us go back to the beginning of nanoscience. This is historical perspective. Any comments? Beginning of nanoscience. I thought I should tell this historical perspective also, besides what we learn for the examination. Beginning. Though the nanotechnology was in use for a long time, there were no systematic studies. That was the problem. They were using blindly. Somebody learned the techniques, they don't know why it behaves, they repeated the same technique, it is passed to the next generations of their own family, right? But they don't know what is actually happening. So when did we start investigating nanoscience or a systematic studies of nanoscience? Then we should start from Richard Feynman. How many of you know this name, Richard Feynman? No one? Did you hear his name? Feynman lectures. You have to. There are books. Feynman lectures on physics. He is very good teacher in physics till today. He got Nobel Prize. I mean, he shared with another scientist Nobel Prize. He's astrophysicist basically. Yeah, he has his skills in multiple places. So Richard Feynman, he was addressing a gathering in the year, let me see, 1959. As he was addressing, he mentioned this: there is a plenty of room at bottom. This is the word he coined then. See, 1959 means long back. There is a plenty of room at the bottom. So what he meant to say is, let me read his statement. I would like to describe a field in which little has been done, but in which an enormous amount can be done in principle. This field, he continued, will not tell us much of fundamental physics, but it might tell us much of great interest about the strange phenomena and that occur in complex situations. What I want to talk about is the problem of manipulating and controlling things on a small scale. It is a staggeringly small world that is below. In the year 2000, when they look back, they will wonder why it was not until the year 1960 that anybody began to move in this direction. That's what his prediction. Then he said there was plenty of room at the bottom. Now, we need to actually go down to the length scales and investigate more. And people wonder why so late. Actually, yeah, good that we started from at least 1960, right? So he also addresses some of the problems in the same meeting. He said, how to put 24 volumes of encyclopedia on a pinhead. Pin is there, pinhead. You want to keep entire library on the pinhead. How do you do it? Because each library is taking so much space. Then he said, solution to the problem is reduce the size. That's what he said. Also, he predicted in the timeline down to the 10 years, next 10 years, all the library might come into a small chip. This much length scale he predicted, and it is like happened already. Okay. So that is the birth of nanoscience. He predicted, then the research started in the direction, we started reducing the length scales. Recently in the Ant-Man movie also, you have to correlate. In the bulk, there seems to be nothing, but if you go to the nano world, there is another kingdom altogether. Okay? Huh. So it is like a new city, new world, new country kind of thing, right? So actually, nanoscience works like that only. If you reduce the particle and see in the quantum region, then new physics applies there. We'll look into what kind of physics will be there in that, right? Yeah. So once he predicted, then in 1971, computer chip is made with the length scale of 10,000 nanometer. Who made this chip? 1971. Computer chip is made by whom? Who is making chips now? ISIS. Who is making? don't know who is making ICs. Everybody, but who is the stronghold? Intel. Intel. Hmm. Intel started making Intel only. Even today, Intel are top. Hmm. So 10,000 nanometer in 1971. Now they reduced it to 65 nanometer in 2003. In 2023, what is the length scale? What is the size that we are talking? Any idea? Hmm? 3? Who made 3 nanometer chip? 4 nanometer. On phone. Which phone, man? Huh? Which phone? 4 nanometer transistor they are using. Chip itself, huh? No, man. 7 nanometer. See, there is a problem. You can't keep on reducing sizes and go. So in 1964, then itself, the co-founder of Intel, Moore, he proposed or predicted something. He said that, okay, today transistor is this much big, but the number of transistors placing on a particular space will double every year. That's what he said. Okay. So today this room occupies only, suppose only one transistor. Next year it becomes 2, then 4, 8, like that, doubles each year. That is his prediction in 1964. Actually, it is being followed till now. If 10 lakhs are there, next year it becomes double, 20 lakhs, then 40 lakhs, like that. Number of transistors are being doubled till today. But there seems to be a cutoff stoppage for Moore's law. ECE background people actually should worry about it. Why Moore's law fails? The people talk about this only. Is Moore's law being continued or it is failing? Can we infinitely go reducing to 20 nanometer, 60 nanometer after 2003, 64, then 20 nanometer, 10, 1 nanometer, like that? Can you go on reducing? That's the question. But that's where physics again comes and interferes. If you keep on reducing the sizes, the physics changes. You are entering unknowingly to the quantum world. Quantum mechanics comes into the play. Then the quantum mechanics, once it comes, everything changes. All the classical physics will not apply. Okay. So once you cross 12 nanometer, the problems come. Boltzmann tyranny, one of the problem. I'm not explaining. Okay. So tunneling happens. Electron suddenly tunnels to the other side. You cannot control. So different problems comes from the quantum physics if you reduce. So simply you cannot reduce. Though you want to reduce, though you have the technology to reduce, physics won't allow. That's where now we are struggling. How do we improve? Is it end for our technology or can we go beyond that? That's why we are struggling. Even Intel is actively looking into it. There seems to be a cutoff for the technology. What if technology stops at that level? We can't advance. All the sophisticated computing, you cannot do it. Chat GPT, you cannot do it in the higher level. Artificial intelligence, you cannot make it. Robotics will not possible. No, all high-end computing applications which requires this kind of transistors, it will not happen if the technology stops. That's where Intel started looking at different alternative solutions. Today, still that problem is there. Though people are Samsung, they said we made 3 nanometer chip. I was wondering, 4 or 3, they claimed. Nothing is in commercial use. Let me tell you. Below 10, nothing is in commercial use. There is a trick actually. Samsung also claimed we made 3 nanometer transistor. I was wondering how could they do it. So if you go back and look carefully about their invention in the original document, there is a image of their transistor that is a basically 70 nanometer in size. But how come you say it is 3 nanometers? They say the performance of this is so that such a way that it works as if it is 3 nanometers. True. That is how, yeah. See, some 10 people are there. I came alone and I did 10 people's work. They say they give the salary of 10 people to me. That's what. So the problems are still the same. Hello, ECU guys. How many are ECUs are there? Can I see your hands? 1, 2. Let me see the hands of ECU. Oh, so many. ECU students. Remember, all computer science students remember, unless they solve this issue, whatever you talk about, IA, GA, GA, nothing is going to work. So students, yeah, not just EC group, but we need to know where we are actually. What are the challenges ahead of us? If you don't know, you don't know where to keep your attention actually. This is very important. So as you go on to your career, you need to identify what are the hot problems or the topics. Then you need to propose some ideas in that direction. If we are touching on the old age thing, I mean, people who are trying and it is not working. Still, if you want to work on that, it may not attract the attention. So even if you move on to the projects, probably as you go on, you need to work on sellable ones. After you do the project, it should be promising. It should offer a good job for you. Okay? It should give attention, and other universities should look at your direction. That kind of projects you have to see. For that, you need to spend some time on what is happening around. That's why I started from historical thing, and now where are and what are the challenges in the nanomaterials. Otherwise, simply reading 1 hour questions and by hearting, writing in the examination makes no sense. Got it? Okay, what is our time now? Over? Not over. 10 minutes is there.